Hello everyone, welcome back to the channel. And today what we will do is we will build up on our previous simulation model of a simple cantilever beam which was elastic. And if you have not already watched that video, it will be great if you can please go and just watch the first video of this series so you can understand and model this beam. And then later in today's video, what we are going to do is we are going to build on that. So before going deep into it, I want to explain to you what we intend today. So this is what we did last time. What we did was we defined a cantilever beam, we fixed it from one end, we applied force on the other end, and then we looked at the elastic deformation behavior of this material. This force was equal to 3000 newtons. Okay, and these are the elastic properties that we provided, and we were looking at the total deformation, stress distribution, strain distribution, and we will change a few things here today. And what I will do now is it is not I am not able to erase, I don't know why, but what I will do is I will create more space. Yeah. So what we want to do now is we want to have the same cantilever beam, but what we will do today is we will do two things. One is that first we will not just define this force, we will define this force a little bit differently, so that, for example, why is it not erasing it? I don't understand this. So that, let's say okay, if this is time and this is force, we want to apply the force, reach the maximum point, and then come back. And this is time 0, this is time 1, and this is force 3000 Newton. Okay, and what it will do is it will allow us to apply a complicated force, like a little bit more complicated, not just force in one direction. It will help us apply this force to a certain limit, and then so load and then unload our beam. And then what we want to do is we want to define not just an elastic beam. So if I say this is strain, this is stress, for now what we have done is we have just defined an elastic beam which has a Young's modulus of 210 GPa in the current case. But what we also want to do is we want to define a plastic beam, which means it can permanently deform if it passes the yield point. And what that means is, you will know from the fundamentals of material deformation or metal deformation that this is the elastic part. That is something that we have defined until now. And after the yield point, we have the plastic deformation behavior of the material, and we will define this as 200 megapascals, and we will define this point as, let's say, 300 megapascals, and this initial plastic strain will be equal to 0, and this final plastic strain will be equal to 1. Okay, and we will define our material like this, and then we will also load it using the same curve, and then unload it, and then we will see if we see a difference in the elastic beam and the plastic beam when we load it, unload it. Okay, so we will use the same geometry, but first we will try to define applied load a little bit differently, and then we will change the material properties, and then we will see if we see a difference there. I hope you understand that. If you don't, then you can comment on this video, and I will try to create a separate explanation of what we are trying to do here, but it is quite intuitive and easy to understand once you will see what we are doing. Okay, so I have this model. We called it canty beam elastic. What I will quickly do is I will copy this model. So you can easily what you can do is you can, once this tree was open, if I click on this minus sign here, I can close this tree. So then my tree becomes neat. I can right click on it, I can click copy model, and then it asks for the name of the copy model. So I will rename it elastic, and I will name it unload. So we will load it and then unload it. Okay, so this model is now copied, and what I can do is now I can open the copied model, and what I want to do is I want to apply the load and unload situation. This is something that we can do here. We have already applied load, but here it was ramp. To apply, because I know that in the steps part we defined the maximum time period to be 1. What we have to do is we have to make an amplitude which will correspond to this configuration of applied force and then not applied force. If I just quickly reconstruct it, then this point will come at 0.5, right? So this means at time 0 force is 0, at time 0.5 force is 3000 newtons, at time 1 force is again 0. So that is what we will define in our amplitude. So I will name it load unload, so I remember it what it is. We will select tabular, I will click continue. We will have this new table where we need to define this. We want to define it for the whole step time. Smoothing is something that we want to use solver defaults for. Amplitude data is time 0, amplitude 0, time 0.5, amplitude 1, which means maximum. I will press tab, I will press enter, and then it will go to the next line. Time 1, amplitude again 0, right? So this is what we have defined here. Amplitude 1 means whatever load we are defining here, it will be multiplied with that amplitude. So here in the load case, in the force case, what I want to do is I want to edit it, and instead of using this amplitude as ramp, I want to use my load unload amplitude here. Okay, so far so good. So this means now it will not just be applied like ramp, it will be applied using this amplitude which we have defined before, and then I press OK. Because I have just changed these two things, I do not need to change the mesh, I do not need to change anything. I will just create a new job for this new model, and I will name it canty beam elastic unload. Okay, so and then I will just select parallelization, similar as before. I will select OK, and then I will submit. So then now we will be able to see the difference in the previous simulation and in the current simulation based on the applied loads. And now you will also see it is taking a little bit more time to complete, but yeah, it is completed. Now I will right click and I will look at the results, and here are the results as before. Now here in this results part, this is our post processor. So in this results part, you will see that in the output database we now have two databases. One was from the previous simulation ODB file, and this one is the current ODB file. The active one is underlined, so I can still go back to the previous one. If I double click this, then that is underlined. So now I am looking at the previous results. If I look at the deformed part and I want to look at the time history, let's look at this. So you will see this. If I just play it once and I play it slow, you will see that how this is deforming when I was applying load, right? So it stops here. Now if I go to the next geometry, I select deformation, and now I see what is happening. So you will see that it will deform and then it will undeform, but it didn't deform that much, probably because the scale factor was results options. No. Common. Yeah. Deformation scale factor is 1. Apply, and I want to see the results again. So now you will see it deforming and then coming back again. I don't know why this is let's bring it here and then run it again. Yeah, so now you will see that after I apply a load, it deforms, and then when the load is released, it is undeformed. So basically what is happening is, because it was elastic, once we unload it, it comes back to its original shape. And we can again see the strains, the stresses. Let's look at the stresses. For now, the stresses are very, very less, but if I increase that, we will see that the stresses here will significantly rise, and then they will eventually come almost back to zero, because it is elastically deforming, right? This is the basic theory that we study. So once a material is elastically deformed, it comes back to its original position. But now we will change our material model, and then the material should undergo permanent plastic deformation, and even if we unload our sample, it will not come back to its original position, and that is what we want to check and look for. And what I will do for that is, I will go back to my model, and you will probably predict that I will just copy this model as a new model, and then instead of defining just elastic, I will also define here plastic mechanical properties. Okay, so I have copied this model. I will open this up, and now what I will do is I will double click on the steel, and I will modify this material. And now in the mechanical, I will go in the plastic part and I will click plasticity. In the plasticity, I am still using isotropic hardening. It is not strain rate dependent, it is not temperature dependent. So the yield stress, interesting point, this is something that we already discussed. So yield point is 200 megapascals with 0 plastic strain, and then when plastic strain will be 1, the yield stress will be, the total stress will be 300 megapascals. So that's what we define here. So yield stress is 200 megapascals and plastic strain is 0. And then our final step is this, and plastic strain is 1. This is just a linear line, but it defines plastic attributes of the material, and we will see how it goes. So now we have defined the plastic properties. Okay. Yeah. So, and now I will create a new job, and what I will do is I will select this cantilever beam plastic unload, and I will okay, continue parallelization, use multiple processors. Now it will take a little bit more time because now it is plastically deforming, and I will click submit. So we do not need to remesh, we do not need to apply new boundary conditions. Everything was all set, so we just changed the material model and we ran the simulations again. So this is also an interesting case because you will see that once you have created a model, you can quickly modify all the attributes and properties and boundary conditions and quickly test which one gives what results. And now we see that our simulation model actually aborted. I want to monitor that, and if you will see here, you will see that once, because now we have defined it to deform plastically, it was not able to converge because of the values that we have defined in our solver. So it went up to 0.6 of the time step, and then once it started unloading, it was not able to converge and it gave an error. To resolve this, what I will do is I will try to go in the step, and what I will try to do here is I will change this number of increments, because I believe this maximum number of increments was reached and therefore it could not continue. I will apply a very big number here, and yeah, let's try to run this again, because I believe that it asks, okay, so it asks if I want to overwrite. Yes, I want to overwrite, and now it is submitted again. And now I will just actively monitor this to see how many increments does it require to reach a certain point, so it is not touching our limit. So yeah, as I was saying, that the simulation models are basically used to quickly modify the materials, apply loading conditions, geometry shapes, and to get an output on what will work best for us in the real world. Okay, so now we see that it completed in total of 36 increments. So yeah, that as I suspected, it was a problem with maximum number of increments we had defined, and now in 36 increments it actually finished, and now we can see the results. Now, ooh. Yeah, that results, options, common, I will select auto compute, apply, okay. And now we will see that how the mesostresses are in the beam. So what will happen is we are loading the beam, it is deforming, and then we unload the beam, it will come back to its original shape more or less, but not completely. So if we look at the deflection, there is still a lot of deflection in the beam. Similarly, if we look at the strains, there are still different types of strains still present within the beam, which means that it did not come back to its original position. If we compare these strains E33 with this beam, we will see that there are negligible, so everything is at very neutral point. This is just numerical instability, nothing more, but these values are in the range of 10 raised to power minus 17. But if you look at this, then these values are quite high, so they are in the range of 0.4 and minus 0.4 ranges, right? So you get the idea that just by changing the material model, we can see that how the beam will behave differently in the elastic range and as well as in the plastic range. So yeah, we will stop our video here, and you can practice by changing the mesh, you can practice by changing the load type or the amplitude that we have defined, and you can also apply material model with more complicated parameters. You can define a material model which is more detailed based on realistic stress strain curves for steel, and you will see better and better results, or the results that will match your hypothesis, or that will match your imagination. So we will stop here now, and in the next sessions, what I will do is I will make some changes about the applied forces and loads, or the plastic parameters that we have defined. And then what we will do is we will look at how we can post-process these results and look at different results in different aspects, and how we can compare the results between these two beams. So yeah, thank you very much, and then see you later. Bye.